This video contains audio content only. There are no visual elements or images accompanying the audio. If you're expecting to see video footage, please note that this is an intentional audio-only presentation. We recommend listening to this content rather than watching the screen. Thank you for your understanding and enjoy the audio. Join us as we unravel the mysteries of superfluidity, a bizarre state of matter where liquids defy gravity and flow without friction. We'll explore this mind-bending phenomenon in simple terms, from its discovery in liquid helium to its potential impact on future technologies. Get ready to dive into the quantum world, where atoms dance in unison and liquids climb walls, revealing the secrets of neutron stars and the promise of frictionless machines. Prepare to be amazed by the strange and wonderful world of superfluidity. Chapter 1. The Mysterious Dance of Liquid Helium. Imagine a liquid that seems to mock the very laws of physics, a substance that slips through cracks thinner than a strand of DNA, scales the walls of its container like a microscopic Spider-Man, and perpetually swirls in a mesmerizing dance. This is the astonishing reality of superfluid helium, a state of matter so bizarre it seems plucked from the realm of science fiction. Liquid helium, cooled to temperatures barely above absolute zero, the point where all atomic motion ceases, transforms into this exotic superfluid. Its most striking characteristic is its complete lack of viscosity. Viscosity, the internal stickiness of a fluid, is what makes honey thick and water flow. Superfluid helium, however, has none of this resistance. It flows without any friction, gliding effortlessly through even the tiniest of openings. This frictionless flow leads to a series of behaviors that seem to defy common sense. One of the most visually arresting demonstrations of superfluidity is the Rollin film phenomenon. Imagine a beaker partially submerged in a bath of superfluid helium. A thin, invisible film of the liquid, just a few atoms thick, starts creeping up the inside wall of the beaker, over the rim, and down the outside. This film, the Rollin film, is formed by the same forces that cause any liquid to cling to a surface, the van der Waals forces. But in superfluid helium, the lack of viscosity allows this film to spread without limit, creating a continuous flow pathway. If the beaker isn't sealed, the helium will continue to creep out until the beaker is empty, as though it has sprung a leak invisible to the naked eye. The indefinite swirling is another hallmark of superfluidity. Stir normal liquid in a bowl, and it will eventually come to rest due to viscosity. Superfluid helium, however, continues swirling indefinitely. But it's not just a continuous rotation. The stirring creates miniature tornadoes within the liquid, known as quantized vortices. These vortices are remarkably stable, maintaining their shape and rotating without dissipating their energy, unlike the fleeting swirls in ordinary fluids. The discovery of this strange state of matter unfolded in the late 1930s, a time of great scientific ferment. In 1937, Pyotr Kapitsa, working in Moscow, noticed liquid helium flowing through extremely narrow capillaries with seemingly no resistance, a clear sign of vanishing viscosity. Simultaneously, John F. Allen and Don Messiner, working at the University of Cambridge, independently observed the same phenomenon. Kapitsa, drawing a parallel to the already known phenomenon of superconductivity, the frictionless flow of electrons in certain materials, coined the term superfluidity. Adding a touch of historical intrigue, it's possible that the first glimpse of superfluidity occurred much earlier, though unrecognized at the time. Heike Kamerlingh-Onnes, the Dutch physicist who first liquefied helium in 1908, may have witnessed the superfluid phase transition in 1911, the very same day he discovered superconductivity in mercury. This tantalizing possibility suggests that one of the most exotic states of matter may have been hiding in plain sight for decades. The lambda point marks a sharp transition in helium force properties, from a normal liquid above it to a superfluid below. The other stable isotope of helium, helium-3, tells a different story. Helium-3 atoms are fermions, particles that obey Fermi-Dirac statistics, which prevents them from directly forming a Bose-Einstein condensate. However, at much lower temperatures, around 2 millikelvin, helium-3 atoms can pair up, forming composite particles that behave like bosons. These pairs then undergo a similar condensation process, leading to superfluidity. This pairing mechanism is reminiscent of how electrons pair up in superconductors, demonstrating a deep connection between the two seemingly disparate phenomena. The strange behaviors of superfluid helium extend beyond simply creeping up walls and swirling indefinitely. As mentioned earlier, the creeping film not only climbs the walls but also coats the entire interior surface of a container. This has surprising consequences. It's as though the liquid is actively seeking an escape route, driven by its inherent tendency to minimize its potential energy. Another striking demonstration involves a cup partially submerged in a bath of superfluid helium. Due to the Rollin film, the helium will creep up the outside of the cup, over the rim, and into the cup, filling it until the levels inside and outside are equal. Conversely, if you start with a cup full of superfluid helium and place it in the bath, the helium will creep out of the cup, dripping from the bottom until the levels equalize. It's a perpetual motion machine of sorts, driven by the unique properties of the superfluid state. Beyond their scientific curiosity, superfluids hold the promise of practical applications. One intriguing possibility is their use as quantum solvents. Because superfluids lack viscosity, they can dissolve substances in a way that's fundamentally different from ordinary solvents. This opens up exciting avenues for studying chemical reactions and other processes at the quantum level. Imagine dissolving a substance in a liquid that has no internal friction, a perfect, undisturbed environment for exploring the intricacies of molecular interactions. Superfluid helium, with its bizarre and counterintuitive behaviors, offers a glimpse into the quantum world at a macroscopic scale. It's a testament to the power of quantum mechanics to produce phenomena that seem to defy our everyday experience, reminding us that the universe is full of surprises waiting to be uncovered. Chapter 2. Bose-Einstein condensation, when atoms sing in unison. This extraordinary transformation is driven by a quantum phenomenon known as Bose-Einstein condensation, BEC. To grasp this concept, we need to delve into the microscopic realm of atoms and their peculiar quantum properties. The building blocks of matter, atoms, and the particles within them, possess an intrinsic form of angular momentum called spin. This isn't a literal spinning like a top, but rather a quantum property that governs how particles interact with magnetic fields in each other. Particles are classified as either bosons or fermions based on their spin. This seemingly minor difference in spin has profound consequences. It's like an exclusive club where each member must have a unique membership card. Bosons, however, are not bound by this restriction. Any number of identical bosons can happily share the same quantum state, crowding into the same energy level like enthusiastic concertgoers rushing to the front row. Now, imagine a gas of boson atoms cooled to extremely low temperatures. As the temperature drops, the atoms lose energy and start to settle into lower energy states. For bosons, this means they can all pile into the lowest energy state available, forming a Bose-Einstein condensate. This isn't just a few atoms sharing a state, it's a macroscopic fraction of them, sometimes even nearly all of them, acting in perfect unison. It's like a choir where all the singers, initially singing different notes, suddenly harmonize on the lowest note, their voices blending into a single, powerful tone. This analogy of a choir can be extended to understand the wave-like nature of BEC. Just as sound waves, originating from different singers, can combine to form a single, coherent wave, the individual wave functions of the bosons in a BEC overlap and merge, creating a single, macroscopic wave function that describes the entire condensate. This macroscopic wave function extends across the entire condensate, giving it a unified, wave-like character. The formation of this macroscopic wave function is the key to superfluidity. In a normal liquid, individual atoms can be easily scattered by imperfections in the container or by collisions with each other, leading to viscosity and energy dissipation. In a BEC, however, the atoms are no longer acting individually. They are all part of the same macroscopic wave function, moving in concert. To excite an atom out of this collective ground state requires a minimum amount of energy. This energy requirement is related to the Landau criterion for superfluidity, which states that a fluid can flow without dissipation only if the velocity of the flow is less than a critical velocity. This critical velocity is determined by the minimum energy required to create an excitation in the fluid. The nature of these excitations, and thus the critical velocity, depends on the strength of the interactions between the particles. In a weakly interacting Beck, like a dilute gas of rubidium atoms, the excitations are primarily sound waves, and the critical velocity is close to the speed of sound in the condensate. In a strongly interacting superfluid, like liquid helium, the excitation spectrum is more complex, featuring not only sound waves, phonons, but also other types of excitations, such as rhodons. This leads to a critical velocity that is generally lower than the speed of sound. The crucial role of particle interactions in superfluidity can be further understood by considering an ideal gas, a hypothetical gas where particles do not interact at all. Even if an ideal gas undergoes Beck, it cannot be superfluid. This is because, without interactions, there's no mechanism to establish a minimum energy for excitations. Any small amount of energy can excite an atom out of the condensate, leading to scattering and dissipation, even at very low flow velocities. The first experimental realization of an atomic Beck, achieved in 1995 with rubidium-87 atoms, was a landmark achievement. To reach the ultra-cold temperatures required for Beck, researchers employed a combination of laser cooling and magnetic trapping. Laser cooling uses precisely tuned lasers to slow down atoms, effectively cooling them. Magnetic trapping then confines the cooled atoms in a magnetic field, preventing them from contacting the container walls and warming up. The rubidium condensate created in this experiment was large enough to be observed directly with a microscope, providing stunning visual confirmation of this long-predicted quantum phenomenon. In this rubidium experiment, as well as in other weakly interacting BECs, the condensate fraction, the fraction of atoms in the condensate, is close to 1 at very low temperatures. However, the superfluid fraction, the fraction of the fluid that flows without dissipation, can be significantly lower, even vanishing in certain cases. This highlights the distinction between BEC and superfluidity, emphasizing that Beck is a necessary but not sufficient condition for superfluidity. In liquid helium, a strongly interacting system, the situation is reversed. The condensate fraction is relatively low, around 0.1 even at absolute zero, while the superfluid fraction is close to 1. Bose statistics play a fundamental role in Beck and superfluidity. Bosons, unlike fermions, are not restricted by the Pauli exclusion principle and can therefore accumulate in the same energy state. This tendency is amplified at low temperatures, leading to the formation of a Beck. The distribution of particles among energy levels, governed by Bose-Einstein statistics, is drastically different from the distribution for fermions, which follow Fermi-Dirac statistics. This difference is crucial for Beck to occur, as it allows a macroscopic number of bosons to occupy the ground state. The two-fluid model, which we'll explore in the next chapter, provides a powerful framework for understanding the unique properties of superfluid helium. This model, based on the idea that superfluid helium behaves as if it were a mixture of two fluids, a normal fluid and a superfluid component, offers a remarkably accurate description of many superfluid phenomena, from the frictionless flow through narrow capillaries to the intriguing thermomechanical effects. The concept of Beck, with its quantum underpinnings, provides a crucial foundation for understanding the nature of the superfluid component in this two-fluid picture. Chapter 3. The two faces of helium, superfluid and normal, partners in a strange dance. Superfluid helium isn't a single entity, but rather a perplexing duet of two intertwined fluids, the enigmatic superfluid and its more conventional partner, the normal fluid. These two components coexist and interpenetrate, engaging in a constant, intricate dance that gives rise to helium II's bizarre and often contradictory behavior. Their proportions shift with temperature, a delicate balance that dictates the character of the fluid. At the extreme cold of absolute zero, helium exists solely as a superfluid. As the temperature climbs, the normal fluid emerges, growing in strength until it completely overtakes its superfluid companion at the lambda point, around 2.17 Kelvin. The superfluid component is where the true magic of helium-2 resides. Its defining characteristic, zero viscosity, isn't just a theoretical concept. It has profound and observable consequences. Imagine pouring a normal liquid through a fine filter. Its viscosity, that internal stickiness, would slow its passage, causing resistance and energy loss. Superfluid helium, however, encounters no such obstacles. It slips through the finest of filters, even those with pores just a few atoms wide, as if the filter wasn't even there. This uncanny ability to penetrate the tiniest cracks and channels, aptly termed superleaks, has been the source of both frustration and fascination for scientists working with liquid helium. This film covers any surface the superfluid touches, creating a pathway for the helium to escape its confinement. Left in an open container, superfluid helium will, via this Rollin film, slowly but surely creep out, emptying itself as if by some invisible force. The Rollin film also explains the peculiar behavior of superfluid helium in interconnected containers. If two containers are connected by a tube, regardless of their relative heights, the superfluid will creep up the walls of one container, across the connecting tube, and down into the other until the levels are equal. It's a striking demonstration of how the superfluid seeks to minimize its potential energy, unhindered by the usual constraints of viscosity. Stirring the superfluid doesn't just create a swirling motion. It gives birth to quantized vortices, tiny tornadoes within the fluid. These vortices are distinct from the fleeting swirls in normal liquids. They are quantized, meaning their rotation is restricted to specific, discrete values, a testament to the quantum nature of the superfluid. These miniature tornadoes are remarkably stable, spinning indefinitely without losing energy, a direct consequence of the superfluid's lack of viscosity. The velocity of the superfluid, a key property in understanding these phenomena, is directly related to the gradient of its phase, a concept rooted in the wave-like nature of quantum mechanics. The phase of the superfluid's wave function, a mathematical description of its quantum state, varies in space, and the rate of this variation determines the superfluid's velocity. In contrast to its ethereal partner, the normal fluid component behaves much like an ordinary liquid. It possesses viscosity, that familiar stickiness that creates resistance to flow. This viscosity can be measured using techniques like oscillating disks. When a disk is immersed in helium-2 and made to oscillate, the normal fluid, clinging to the disk, resists the motion, causing the oscillations to dampen. The rate of this damping provides a direct measure of the normal fluid's viscosity. The normal fluid is also responsible for other dissipative processes, converting the kinetic energy of motion into heat, just like in any ordinary liquid. Moreover, the normal fluid carries entropy, a measure of the disorder in a system. This entropy is associated with the thermal excitations in the liquid, the microscopic vibrations and movements of the helium atoms. The interplay between these two disparate components is what gives helium-2 its unique character. At absolute zero, the helium exists entirely in its superfluid state, a perfectly ordered quantum liquid. As the temperature rises towards the lambda point, the normal fluid fraction increases, introducing disorder and viscosity into the system. This change in the balance between the two components is not gradual but rather exhibits a sharp transition at the lambda point, reflecting a fundamental change in the helium's microscopic structure. The fountain effect, a dramatic demonstration of the two-fluid model, vividly illustrates this interplay. When heat is applied to one side of a container filled with helium-2, the superfluid component, driven by its tendency to minimize temperature differences, rushes towards the heat source. Simultaneously, the normal fluid, carrying the entropy and heat, flows away from the heat source. This counterflow creates a striking fountain of helium, shooting upwards as if defying gravity. Another fascinating manifestation of the two-fluid model is second sound. Unlike ordinary sound, which is a pressure wave, second sound is a temperature wave. It propagates through helium-2 by oscillations of the superfluid and normal fluid densities. Imagine a pendulum swinging back and forth. In second sound, the superfluid and normal fluid densities oscillate in a similar fashion, creating a wave of temperature that travels through the liquid. Early evidence for the two-fluid model came from the ingenious Andronikashvili experiment. A stack of closely spaced disks was suspended in helium-2 by a torsion fiber and made to oscillate. As the temperature changed, so did the proportion of superfluid and normal fluid. Only the normal fluid, due to its viscosity, was dragged along with the oscillating disks, effectively changing the system's moment of inertia. By measuring the period of oscillation at different temperatures, Andronikashvili could determine the temperature dependence of the normal fluid density, providing crucial support for the two-fluid model. The unique properties of helium-2, born from this strange dance of two fluids, have found valuable applications. Its exceptional cooling abilities, a consequence of the superfluid's high thermal conductivity and the normal fluid's ability to carry heat away, make it an ideal coolant for superconducting magnets, which require extremely low temperatures to operate. The stability and frictionless flow of the superfluid component also make it suitable for use in high-precision gyroscopes, devices that measure rotation with extreme accuracy. Superfluid helium, with its two-fluid nature, offers a remarkable window into the quantum world. It's a testament to the power of quantum mechanics to create phenomena that challenge our intuition and inspire further exploration. A constant reminder that even in the seemingly simple world of liquids, there are depths of complexity yet to be plumbed. Chapter 4. Whispers from the Cosmos. Superfluidity in neutron stars and the secrets of the universe. Imagine a star unlike any other, a celestial object so dense that a single teaspoon of its material would weigh billions of tons on Earth. This cosmic heavyweight, a neutron star, spins with dizzying speed, a consequence of its dramatic birth from the collapsed core of a massive star. Born in the fiery heart of a supernova explosion, a neutron star represents the ultimate triumph of gravity over matter, crushing the core of a once mighty star into an object barely the size of a city. But the story of a neutron star doesn't end with its dramatic collapse. Within its seemingly simple exterior lies a complex layered structure, a cosmic onion with layers of exotic matter. The outermost layer, the crust, is a rigid lattice of neutron-rich atomic nuclei, a solid foundation for this extreme object. Beneath the crust lies the outer core, a realm of bizarre quantum phenomena. Here, under the immense pressure and chilling temperatures, neutrons, the neutral particles usually confined to atomic nuclei, break free and form a sea of superfluidity. And deeper still, in the mysterious inner core, lies matter of even more exotic forms, perhaps hyperons or even deconfined quarks, a state of matter we can only theorize about. The extreme conditions within a neutron star's outer core, pressures millions of times greater than at the Earth's center and temperatures a fraction of a degree above absolute zero, create an environment ripe for superfluidity. Just as electrons in some terrestrial materials pair up at low temperatures to create superconductivity, allowing electricity to flow without resistance, so too do neutrons in a neutron star. However, instead of pairing with another type of particle, the neutrons themselves, driven by the strong nuclear force, overcome their natural repulsion at close range and form pairs. These pairs, known as Cooper pairs, behave like bosons, particles with integer spin that can condense into the same quantum state, creating a superfluid. This idea, that neutrons within a neutron star could form a superfluid, was first proposed by Arkady Migdal in the 1950s, a pioneering insight that opened a new window into the behavior of matter under extreme conditions. Migdal realized that the strong nuclear force, while typically repulsive at very short distances, could become attractive at slightly larger separations, allowing neutrons to form Cooper pairs. This delicate balance between repulsion and attraction is crucial for the formation of the neutron superfluid. The presence of this superfluid core has profound implications for a neutron star's behavior. The superfluid, decoupled from the star's crust and rotating independently, can dramatically affect the star's spin. One of the most intriguing consequences of this superfluid core is the phenomenon of glitches, sudden increases in a pulsar's spin rate. Pulsars, rapidly rotating neutron stars that emit beams of radiation, are like cosmic lighthouses, their regular pulses providing a precise measure of their rotation. Occasionally, these pulses experience a sudden speed up, a glitch, followed by a gradual relaxation back to the original spin rate. These glitches are thought to be caused by the interaction between the superfluid core and the crust. As the crust slows down due to electromagnetic radiation, the superfluid core, spinning faster, transfers some of its angular momentum to the crust, causing a sudden spin up. By studying these glitches, astronomers can probe the interior of a neutron star, gleaning information about the properties of the superfluid and the dynamics of this complex system. The interplay between the superfluid neutrons and the other components of the neutron star's core creates a complex dance of interacting superfluids. One fascinating aspect of this interaction is the phenomenon of entrainment. As a neutron moves through the superfluid, it drags along a cloud of protons, a consequence of the strong nuclear force. This entrainment affects the distribution of charge within the star, influencing its magnetic field and creating a complex interplay between the superfluid neutrons and the superconducting protons in the outer core. This interaction can also affect the star's oscillations, creating a rich spectrum of vibrational modes that could potentially be observed. Within the neutron superfluid, another layer of complexity arises with the formation of vortices, similar to those seen in liquid helium. However, unlike the vortices in liquid helium, these neutron star vortices are likely magnetized due to the entrained protons. These magnetized vortices can interact with the charged components of the star's core, leading to energy dissipation and potentially playing a role in the long-term evolution of the star. This interaction between vortices and the surrounding matter could manifest in observable effects, such as changes in the star's electromagnetic emissions. The possibility of exotic matter in the inner core adds another layer of intrigue to the neutron star puzzle. While the outer core is thought to consist primarily of superfluid neutrons and superconducting protons, the immense pressure at the star's center could give rise to even stranger forms of matter. Hyperons, particles containing strange quarks, or even a quark-gluon plasma, a state of matter where quarks and gluons are no longer confined within protons and neutrons, might exist in this extreme environment. The interaction between these exotic forms of matter and the superfluid outer core remains an open question, a tantalizing mystery for future research. For instance, it is theorized that the abrupt changes in the rotational speed of neutron stars, known as glitches, are caused by the interaction between superfluid vortices and the crust. This offers a unique opportunity to simulate and study these extreme phenomena in laboratory settings. Neutron star superfluidity, a consequence of the strong nuclear force and the extreme conditions within these collapsed stars, offers a unique laboratory for studying fundamental physics. It connects the microscopic world of quantum mechanics, where particles can be in multiple places at once and behave like waves, to the macroscopic scale of astrophysical objects, where gravity reigns supreme. By studying these extreme systems, we can gain insights into the fundamental forces of nature and the behavior of matter under conditions far beyond what we can replicate on Earth. The whispers from these distant stars, carried by their subtle variations in rotation and electromagnetic emissions, hold secrets about the universe and the very fabric of reality. Chapter 5. The Expanding Universe of Superfluidity, Beyond Helium. The story of superfluidity, as we've seen, begins with the strange, frictionless dance of liquid helium near absolute zero. But the tale doesn't end there. It extends beyond the confines of cryogenic helium, reaching into the realm of exotic materials and pushing the boundaries of our understanding of quantum mechanics. Our journey now takes us to the frontiers of physics, where scientists are creating and exploring new forms of superfluidity in ultra-cold atomic gases, exciton polaritons, and other exotic materials. Imagine a cloud of atoms, so cold that they barely move, trapped and suspended in a vacuum by invisible forces. This is the world of ultra-cold atomic gases, where temperatures plummet to billionths of a degree above absolute zero, a realm far colder than the depths of interstellar space. Achieving these nanokelvin temperatures requires a combination of cutting-edge techniques. Laser cooling, the first step, uses precisely tuned lasers to slow down atoms, like gently pushing a swing at just the right moment to reduce its motion. These lasers act like a viscous medium, slowing the atoms and cooling the gas. But laser cooling alone isn't enough. To reach the extreme cold needed for superfluidity, another technique, evaporative cooling, is employed. Imagine a cup of hot coffee. The most energetic molecules escape as steam, carrying away heat and cooling the remaining coffee. Similarly, in evaporative cooling, the most energetic atoms are allowed to escape the atom trap, lowering the average energy and temperature of the remaining atoms. The trap itself is often a magnetic trap, which uses magnetic fields to confine the atoms, like an invisible cage preventing them from touching the container walls and warming up. In these ultra-cold gases, scientists have observed both bosonic and fermionic superfluidity. Bosonic superfluidity, as we've seen in helium-4, arises when bosons condense into the same quantum state, forming a Bose-Einstein condensate, BEC. This condensate behaves like a single, giant atom, flowing without friction. Fermionic superfluidity, however, is a more subtle and challenging phenomenon. Fermions are forbidden from occupying the same quantum state. So how can fermions become superfluid? The answer lies in the formation of Cooper pairs, a concept borrowed from the theory of superconductivity. Two fermions, despite their natural repulsion, can bind together at very low temperatures, forming a composite particle that behaves like a boson. Imagine two shy dancers, initially hesitant to approach each other, but drawn together by a subtle, attractive force. Once paired, they move in perfect harmony, gliding across the dance floor as one. These Cooper pairs, now bosons, can condense into the same quantum state, just like their bosonic counterparts, and exhibit superfluidity. Creating fermionic superfluids in ultracold gases is a delicate balancing act. The strength of the interaction between fermions can be tuned using a technique called Feshbach resonance. By applying a magnetic field, researchers can adjust the interaction strength, making it more attractive and promoting the formation of Cooper pairs. This tunability allows scientists to explore different regimes of fermionic superfluidity, from the weakly interacting BCS regime, where Cooper pairs are large and loosely bound, to the strongly interacting Beck regime, where Cooper pairs are tightly bound and resemble molecules. Specific examples of fermionic superfluids created in the lab include lithium-6 and potassium-40. These isotopes, with their odd number of nucleons, are fermions. By cooling these gases to nanokelvin temperatures and tuning the interactions using Feshbach resonance, researchers have created fermionic superfluids, observing their characteristic frictionless flow and vortex formation. The ability to tune the interaction strength also allows for the study of the Beck-BCS crossover, a smooth transition between the BCS and Beck regimes. As the interaction strength increases, the fermionic superfluid evolves from a BCS-like state with loosely bound Cooper pairs to a Beck-like state with tightly bound molecules. This crossover provides a unique opportunity to study the interplay between these two distinct regimes of superfluidity. Now, let's shift our focus to another exotic realm where superfluidity has been observed: exciton polaritons. These intriguing entities are not atoms or molecules, but quasi-particles, hybrid particles that are part light and part matter. They are created in semiconductor microcavities, tiny sandwich structures where a thin layer of semiconductor material is placed between two highly reflective mirrors. When light enters this microcavity, it bounces back and forth between the mirrors, interacting strongly with the electrons and holes in the semiconductor. This strong coupling between light and matter gives rise to new quasi-particles, the exciton polaritons. Imagine a photon, a particle of light, trapped in a hall of mirrors, constantly interacting with the material of the mirrors. This interaction creates a hybrid particle, part light, part matter, that inherits properties from both its parents. The exciton polariton has a very small effective mass, much lighter than an atom, which makes it easier for them to condense into a Beck, even at relatively high temperatures. Furthermore, their partially photonic nature allows for easy optical probing, making them ideal candidates for studying superfluidity. Exciton polariton superfluids offer several advantages for studying this exotic phenomenon. Their relatively high transition temperatures, compared to helium or ultracold atoms, make them more accessible experimentally. In some cases, exciton polariton superfluidity has been observed at temperatures approaching room temperature, a remarkable feat that opens up the possibility of developing superfluid devices that operate under normal conditions. The ease of optical probing also allows for direct visualization of the superfluid flow and the formation of quantized vortices, providing valuable insights into the nature of superfluidity. Specific examples of observed superfluid phenomena in exciton polariton systems include frictionless flow, quantized vortices, and persistent currents. In frictionless flow experiments, exciton polaritons are made to flow past obstacles, and their motion is observed to be undisturbed, a clear signature of superfluidity. Quantized vortices, the tiny tornadoes we've seen in helium, have also been observed in exciton polariton superfluids, confirming their quantum nature. Persistent currents, flows that continue indefinitely without any external driving force, have been created and observed, demonstrating the remarkable stability of these superfluids. Despite these successes, the field of exciton-polariton superfluidity is still full of challenges and open questions. One of the key differences between exciton-polaritons and other superfluids is that exciton-polaritons are inherently non-equilibrium systems. Due to the constant leakage of photons from the microcavity, the system needs to be continuously pumped with energy to maintain the superfluid state. This drive and dissipation, absent in equilibrium superfluids like helium, play a crucial role in the behavior of exciton-polariton superfluids and are still not fully understood. The quest for room temperature superfluidity in these systems is another major challenge. While some progress has been made, achieving robust, stable superfluidity at room temperature remains a significant hurdle. The search for superfluidity extends beyond ultracold atoms and exciton-polaritons. Other exotic materials are being investigated, each with its unique properties and challenges. For instance, magnon-polariton condensates, hybrid particles that are part light and part magnetic excitations, magnons, have been created in magnets, and their superfluid properties are being actively explored. These condensates offer a new platform for studying superfluidity in a solid-state system, with potential applications in spintronics and quantum information processing. The quest for superfluidity in these exotic materials is a journey into the unknown, a testament to the power of human curiosity and ingenuity. It's a reminder that even in the seemingly well-understood world of condensed matter physics, there are still mysteries to be unraveled and new frontiers to be explored. The ongoing search for superfluidity is not just a quest for a new state of matter. It's a search for a deeper understanding of the quantum world and the fundamental laws that govern our universe. Chapter 6. The Quantum Frontier. Harnessing the power of superfluids for future technologies. Imagine a world where lasers aren't just beams of light, but beams of atoms, flowing with perfect precision, enabling measurements of exquisite accuracy. A world where computers harness the bizarre laws of quantum mechanics to solve problems deemed impossible today. A world where frictionless machines whisk us across the globe and into space, powered by the very essence of quantum fluidity. This is the potential of superfluids, a quantum frontier brimming with wonder and possibility. Our journey begins with the atom laser, a device that sounds like science fiction but is rooted in the very real and very strange world of quantum mechanics. Just as a conventional laser emits a coherent beam of photons, light particles all oscillating in perfect unison, an atom laser emits a coherent beam of atoms, all in the same quantum state, marching in lockstep. This coherence, this quantum harmony, is the key to the atom laser's power. Think of a marching band, each member stepping in perfect time, their instruments producing a single, unified sound. This is analogous to the atoms in an atom laser beam, all moving with the same momentum and energy, their wave functions overlapping and merging into a single, macroscopic wave. This coherent beam can be focused with incredible precision, offering a new level of control over matter at the atomic scale. This precision opens doors to a world of ultra-accurate measurements. Atomic clocks, the timekeepers of our modern world, could become even more precise, their accuracy improved by orders of magnitude. This leap in timekeeping precision would not only enhance global navigation systems but also enable more sensitive tests of fundamental physics, pushing the boundaries of our understanding of the universe. The manufacturing of electronic chips could also be revolutionized. The atom laser's focused beam could be used to etch circuits with atomic precision, creating smaller, faster, and more powerful electronic devices. But the atom laser's potential extends beyond precision engineering. Researchers have used sodium atoms, cooled to near absolute zero and formed into a beck, to slow down light, even stopping it completely. This, frozen light, stored within the atomic cloud, can be released on demand, opening up exciting possibilities for telecommunications and data storage. Imagine storing and retrieving information encoded in light pulses, manipulating light itself as a medium for computation. Even more dramatic effects have been observed in these ultra-cold atomic gases. By manipulating light and sound within the condensate, researchers have created superfluid analogues of shock waves and tornadoes, miniature versions of these powerful phenomena unfolding at the microscopic scale. These dramatic excitations, far from equilibrium, give rise to rich excitation dynamics, revealing the intricate interplay of sound and light in this quantum fluid. The formation and decay of solitons, solitary waves that maintain their shape as they travel, and the creation of quantized vortices, miniature tornadoes with quantized rotation, offer a glimpse into the complex choreography of this quantum world. The quantum frontier extends beyond the atom laser. Superfluids, with their unique properties, hold immense promise for quantum computing, a revolutionary technology poised to transform our world. Quantum computers, unlike their classical counterparts, rely on the principles of quantum mechanics to perform calculations. The basic unit of information in a quantum computer is the qubit, a quantum bit that can exist in a superposition of states, both 0 and 1 simultaneously. Superfluids, with their inherent coherence, could be the key to creating and manipulating these qubits. Imagine a superfluid as a quantum playground, where qubits can be created and manipulated with exquisite control. The lack of dissipation in superfluids, their ability to flow without friction, could minimize errors in quantum computations, a major hurdle in current quantum computing technology. Furthermore, superfluids could be used as a quantum solvent, dissolving substances and allowing for their manipulation at the quantum level. This opens up new possibilities for materials science and chemistry, enabling the creation of novel materials and the study of chemical reactions at the quantum level. The unique rotational properties of superfluids also offer exciting possibilities for high-precision gyroscopes, devices that measure rotation. Unlike conventional gyroscopes, which rely on the inertia of a spinning wheel, superfluid gyroscopes exploit the quantum properties of the superfluid. One striking example is the Hess-Fairbank effect, where a superfluid, initially rotating with its container, comes to rest when cooled below the lambda point, a consequence of the superfluid's unique response to rotation. Another key feature is the formation of quantized vortices, miniature tornadoes within the superfluid. These vortices, with their quantized rotation, can be used to create extremely sensitive gyroscopes, capable of detecting even the slightest changes in rotation. These superfluid gyroscopes could revolutionize navigation, both on Earth and in space, providing unparalleled accuracy and stability. They could also be used to test fundamental theories of physics, such as Einstein's theory of general relativity, probing the nature of gravity and the curvature of spacetime. Moreover, these superfluids, with their unique sensitivity to external perturbations, could be used as detectors of exotic particles, opening up new avenues for exploring the universe at the subatomic level. Superfluidity's potential extends beyond precision measurement and quantum computing. The ability of superfluids to transport energy and information without dissipation opens up exciting possibilities for new types of electronics. Imagine electronic circuits where electrons flow without resistance, generating no heat and wasting no energy. This could lead to more efficient and powerful electronic devices, revolutionizing everything from smartphones to supercomputers. Superfluid electronics could also enable the development of new types of energy transport systems, where energy is transmitted with minimal loss, paving the way for a more sustainable energy future. Superfluids have also found valuable applications in more established technologies. Their exceptional cooling abilities make them ideal coolants for high-field magnets, which require extremely low temperatures to operate. These magnets are used in a variety of applications, from medical imaging, MRI, to scientific research, particle accelerators. Superfluids are also used as detectors of exotic particles, providing a sensitive probe for studying the fundamental constituents of matter. The link between superfluidity and high-temperature superconductivity is another area of active research. While the mechanisms behind high-temperature superconductivity are still not fully understood, superfluidity offers valuable insights. The pairing of fermions, a key element in both superfluidity and superconductivity, suggests a deep connection between these two phenomena. Studying superfluidity in ultra-cold atomic gases and other exotic materials could help unravel the mysteries of high-temperature superconductivity, paving the way for materials that can conduct electricity with zero resistance at or near room temperature. The quantum frontier, with its superfluids and other exotic states of matter, is a realm of endless possibilities. From atom lasers and quantum computers to frictionless machines and novel materials, the unique properties of superfluids hold the key to unlocking a new era of technological innovation. It's a journey into the unknown, driven by human curiosity and ingenuity, a testament to the power of quantum mechanics to transform our world in ways we can only begin to imagine. Superfluidity, the frictionless flow of matter, isn't just a quirk of liquid helium. From neutron stars to ultra-cold atomic gases, this quantum phenomenon reveals itself in diverse systems, offering a window into the bizarre world of quantum mechanics at a macroscopic scale. Its study has broadened our understanding of fundamental physics, with potential applications ranging from ultra-precise measurement to quantum computing and frictionless machines. This research is pushing the boundaries of technology, promising innovations that could reshape our world. What marvels of superfluidity will we uncover next? Share your thoughts and questions below. Like and subscribe for more explorations into the fascinating world of science. Never stop learning.